Okay, so since it is already 3 o'clock, we'll get started with the session. So, welcome everyone to week 10 of this TA session of this course Optical Spectroscopy and Microscopy Fundamentals of Optical Measurements and Instrumentation. And as you all know, I am Arjun, and I am the TA for this course, who is presenting over all of your TA sessions for the past 10 weeks and will be doing so for the next two sessions as well. So, uh, as we all know, the routine will be simple this time as well. So, we'll be starting with a recap of what happened in the lectures for week 10, followed by which we'll be discussing over some sample problems. And after discussing the sample problems, we'll also be going over previous week's assignment questions. So, in between, there will also be small gaps for doubt sessions. So, if you guys have any doubts, you feel free to ask them. So, we'll get started right away. Once again, just yeah. So, as we all know, the um, main aim of this course is to understand optical spectroscopy, how optical spectroscopy works, and how we are going to use it in applications of how we are going to use the optical excitation and emission phenomena to use them in biological, not biological instruments which can be used to image biological phenomena, which is specifically a microscope, and how we can construct different kinds of microscope to image whatever biological specimens we have in hand. And week 10 is kind of a more week 10 more ventures more into the application parts where the course instructor Dr. Balaji Jayaprakash um, explains more in detail about microscopes and different kinds of microscopes, particularly focusing on confocal microscope and how one photon and multi-photon excitation happens. So we kind of started off from where we left off last week line, where in week 9 we saw about the concepts of your optical hinge points as well as your spatial and temporal focus. And we also saw this week we were kind of continuing into the same concept where we saw that before starting any microscopic experiment, how we need to make sure that the beam width is aligned to the specimen of our choice in order to image the biological specimen completely. And generally, microscopes used kind of finite optics where image was kind of formed at a fixed distance from the objective. And we kind of saw how modern systems use infinitely corrected objectives where we saw a parallel beam of light which is being produced by this infinitely corrected objectives rather than converging lenses. So this parallel path of beam of light is highly advantageous because it kind of allows us or any researcher to insert any other uh, subsequent optical elements such as your tube lens or your dichroic mirrors and filters and the path. And it doesn't the main advantage of doing this is despite doing this it doesn't introduce any anomalies or aberrations or change in the image positions. And these are the typically the advantage of your um, infinitely corrected objective lens. And in the later parts of the lectures, we also saw we had a brief comparison about how one photon excitation happens, which is used in conventional microscopic techniques, and what are all the demerits, limitations of one photon excitation techniques, with which we need to counteract with using multi-photon excitation process, typically your two photon as well as your three photon excitation processes. Mainly, we use this multi-photon excitation processes to kind of some image deep tissues, image any chromophore in deep tissues, as well as to image any fluorophore which is excited in the UV region or in the near UV region. So for this purposes, we use this two photon or this multi-photon excitation processes. And in the fag end of the week's lectures, we also saw more about microscopic lenses, how different types of lenses are combined with different types of objective lenses to kind of arrive at different kind of magnification. And in the lectures, we also saw about three different kinds of lens, which is made by your different brands such as your Nikon and Carl Zeiss and all this stuff. So all of these are based on the concept of infinitely corrected objectives which produce your parallel rays. Uh, the one thing that we need to note about this thing is that they can't form an image on their own, and they must be combined with a tube, something called as a tube lens, in order to converge the light onto the sensor. So the infinitely corrected objective lens will just produce a parallel beam of light from the focal length. You need something such as a tube lens, which is present in this diagram as you can see, to converge the parallel beam of the rays into a specific point. So this tube lens is what we saw in detail in the later part of the lectures, where we saw about focal lengths and as well as different types of brands and what type of standardized focal lens they use for their tube lenses. We had different kinds of brands such as like Nikon, Olympus, as well as your Carl Zeiss. And we also saw how to kind of read the inscriptions made on this type of lenses, uh, particularly how they mentioned all of them in the same pattern, as in how they mentioned the magnification first, followed by the numerical aperture, and followed by whether they use any immersion or not, and what kind of region of the optical wavelength they are usually imaged in. So those kind of stuff we saw in the in these lectures, and we also saw about other subsequent auxiliary parameters such as your correction level and inscription of other parameters like your apo and all those stuff, which includes for apochromatic, which represents the highest level of correction for your chromatic as well as your spherical operations. And in the end, we also saw how to calculate magnification based on the focal length of your objective lens as well as your tube lens. So basically, it will be the ratio of the tube lens's focal length to the objective lens's focal length. So for example, if we have a 25x magnification, so 25x just means that the focal length of the tube lens is 25 times more than the focal length of the objective lens. So that's all the concepts that were discussed in the week 10's lectures, and I think in week 11 and week 12 we will be going more in sorry, we'll be going more in detail to discuss about the all of these concepts in a typical laboratory setup. So we can have a short doubt session here, but since no one is there in the room, I'll just wait for like 1 or 2 minutes for someone to join, and maybe then we can proceed to discuss about the uh, problem statements, sample problem statements. Okay, we'll get started with the sample problems. Let's just hope that someone joins the class as soon as we move on. So, most of the problems, because the only numerical problems that I will come across for week 10 are mostly the magnification, which I think people can easily find around because it's just a ratio and it's just simple math. So, I'm not going to go in detail about the mathematical problems this week as well. Instead, we'll just focus on simple theoretical questions that can come across in your exam. So, question number one is, what is the standardized tube lens focal length used by Nikon and Leica? And this is kind of a straightforward question. The answer is 200 millimeter. So we saw that different brands uses different standardized focal lengths lenses. Uh, One of which Nikon and Leica use 200 millimeter lens, and other brands such as your Olympus uses like 180 millimeter, and some other brands use 165 as well as 160 millimeter. Yeah. So, question number two, an objective lens marked with plan. Actually, I think it's supposed to be, I think it's plan only. Is specifically corrected for which optical defect? An objective lens marked with is specifically corrected for which optical defect? Field curvature, chromatic aberration, spectral mismatch, and energy defacing. And I think I've just purposefully gave all um, foreign concepts to us because all three of them, like at least two of them, we haven't actually came across so far. So the answer is option A, just field curvature, providing a flat field. So third question is what we kind of discussed in the recap section as well. In an infinitely corrected microscope system, what is the state of the light beam after it passes through the objective lens? In an infinitely corrected microscope system, what is the state of the light beam after it passes through the objective lens? People need to remember that there is no involvement of tube lens so far. So light comes from the sample and then it passes through the objective lens. So basically it's going to go parallel. So all the light rays which are going to emanate from the focal point of the specimen, they are going to go parallel. So the correct option is option B. It consists of parallel rays, imaged at infinity, and we need a subsequent tube lens which we need to keep in place to kind of image the to converge the parallel beam into a focal region. And this also we saw in the recap section. What is the apo inscription on a lens barrel represent? And the option, obvious option, like straightforward option here is option number D, which is apochromatic correction, which is the highest correction for chromatic and spherical aberrations. Okay, this one is probably something which we haven't discussed in the uh, recap section. Is probably coming from the second video of the lectures. Which one of the following describes color elimination? Which of the following describes your color elimination? So options given are: it images a uniformly illuminated diaphragm onto a sample. It images the light source filament directly onto the sample. It produces artificial contrast across the center of the image. It requires the removal of the condenser lens. And the correct answer here will be option number A. It images a uniformly illuminated diaphragm onto the sample. I hope people are clear with the question. So I'll go with the next question. If this is also a straightforward question, but we just haven't discussed in the recap. If a lens is marked with the letter W, what immersion medium must be used? So we saw that apart from the magnification and the numerical aperture, as well as the region in which it will be the region in which the objects will be imaged in, the wavelength region in which the objects will be imaged in, they will also be provided with a letter or no letter at all. So the letter W is corresponding to water immersion. So the correct option here is option B, water. So you can also use oil immersion, or you could not use any immersion medium at all, at which point there will just be a dash mark on the immersion medium place, which just means that it is no immersion or air immersion. So it just uses the air medium around us to be used as an immersion medium. But on the other hand, for this question at least, if any lens is marked with W, it means that the water immersion medium must be used. Next question. How is the magnification of a modern microscope objective determined? So this also we saw in the um, recap section. So the magnification of a modern microscope is calculated by the ratio of your tube lens to your objective lens. So the correct option is option B. Focal length of tube to focal length of the objective. Next question is, why is critical illumination generally avoided in advanced microscopy? Why is critical illumination generally avoided in advanced microscopy? Options given are it makes the image too bright, it requires too many lenses, it images the light source filament onto the sample creating an uneven background, it only works with UV light. So the correct option here is option C, which critically illumination images the light source filament onto the sample, so which creates an uneven background. So that is generally avoided in advanced microscopic techniques. Yeah, this is also a pretty straightforward question. So, what is the numerical aperture of a lens determine? What is the numerical aperture of a lens determine? Whether it determines the resolution and light gathering power, whether it determines the total length of the microscope, the color of the laser beam, or the weight of the objective. And pretty much the most straightforward answer, as you all know, where the numerical aperture formula is being used is the resolution and the light gathering power. So that is what the numerical aperture signifies. And this also we saw in the recap as well as in the lectures. Uh, what is the most effective safety practice when working with high power lasers in a lab? What is the most effective safety practice when working with high power lasers in a lab? And we saw that one of the most important safety practices with working with high power laser is to keep the alignment in check. So we have to develop alignment habits that keep the eyes out of the beam plane. So all of these questions are pretty straightforward questions, which uh, I think that's all the sample problems that I have for today. So we can have one more short doubt session before we start discussing the week nine's assignment answers. Week nine's assignment questions and answers. Okay, then we can start with the sample problem discussion. So, confocal microscope works by what? Confocal microscope, we have four options for that. Confocal microscope basically works through either selective excitation of focal point or turning on and off the detector when point of interest is not in focus, reducing the fluorescent emitted light which is originating or not originating from the focal point with the pinhole aperture. Yeah. So basically, confocal microscope, as we know, it's a very it's a focal point based technique, and if you compare all the other options, if you can see that the regular microscopy technique also does. So what a confocal microscope does is it reduces the fluorescent light which is not originating from the focal point of the objective lens, basically usually where our sample is kept with the pinhole aperture. So all those light can't pass through the pinhole aperture except for the object in focus or the sample in focus. So all this background light is reduced. So the correct option is option number D. Sorry, option number C. Question number 2. While using a confocal microscope to obtain an image of fluorescent object, if the student moves the pinhole aperture away from the correction lens by distance x from the focal point of the lens, then what happens to the this thing? So basically, the pinhole aperture is moved away from the correction lens by a distance x. So basically, what it means that the focal point is kind of moved by a specific distance. So accordingly, the uh, image also will be like image also will be obtained based on the position of the focal point of the lens. So it will be varying by a specific factor which is called as scaling constant. So the correct answer is option number C. Image of the point source at distance alpha x, where alpha is the scaling constant away is obtained. Fluorescence intensity less than at focal point. Third question, while obtaining a Z-stack image using a confocal microscope, it's best to move only the objective ends up or down while the pinhole aperture is not moved. Only the pinhole aperture up or down while the objective is not moved. Both the objective and pinhole aperture up or down can be moved related to each other. It's not possible to obtain Z-stack images because the confocal microscope gives only the image from a focal point light source. And it's a pretty much obvious answer if you are working with microscope. So both the objective and the pinhole should be moved related to each other. Yeah. So the correct option is option C for a Z-stack image. So question number 4. In an experiment to obtain an image of a fluorophore stained sample, a suitable emission filter to use where excitation maxima is 480 nanometer, spectra range is 450 to 510 nanometer, emission maxima is 540 nanometer, and spectra range is 500 to 580 nanometer. So the correct emission filter is 520-40 band pass filter. So going to the next question. For a microscope with a resolution limit of 100 nanometer, the best sampling rate while scanning the sample object to obtain the image is what? So the best sampling rate here will be slightly less than 50 nanometer. So the sampling rate should always be less than or equal to half the resolution limit. So, or how to say is the resolution limit should always be greater than, usually what we saw in the last week's classes, the resolution limit should always be greater than or equal to twice the sampling rate. So if the resolution limit is 100 nanometer, then it should be uh, less than or equal to half the twice the sampling rate. So it should be slightly less than 50 nanometer. Half of 100 nanometer is 50, so it should be slightly less than that. So it's slightly less than 50 nanometer. Okay, so this is a multiple select question, which means more than one option can be correct. In the optical hinge point concept, which one of the below options is denoted as a optical hinge? Point in space where about which the beam is moving, the incident beam, the momentum of the photons change while the density does not change with respect to time, and material of the lens. And the correct option is options A and C, where the optical hinge point is denoted by the point in space where the beam is moving, as well as the momentum of the photons change while the density does not change with respect to time. Okay. Uh, let's assume a laser pumps. Let's assume a laser pump 1064 nanometer wavelength of light after SHG. So SHG just means second harmonic generation. This wavelength would be in watt nanometer. So after second harmonic generation, if you have to find the wavelength, you just have to divide the. It's a numerical question, so you have to enter the answer. So if you want to find the wavelength after second harmonic generation, you just have to divide it by 2. So the answer will be 1064 divided by 2, which will be 532 nanometer. Subsequently, for their subsequent harmonic generations, you just have to divide the total wavelength by the corresponding n factor, which is 2 or 3 or whatever it is. In this case, is the second harmonic generation, which is denoted by SHG. So you have to divide 1064 divided by 2, which will give you 532. Okay. Choose the suitable options for the above optical setup. So it's a confocal fluorescence microscope diagram. So here we have 5 options detected and all the samples detected, and we have to kind of see which one corresponds to which option. So as we can see, in all the 4 options, the option 1 is detected, which is kind of not which is not debatable at this point. So we have to find out what the other 2, 3, 4, 5 signifies. So 3, we can see that from all the previous lectures we can see that 3 is the dichroic mirror. So pretty much options 3, options 2 and 4, which says that option 2 is the dichroic mirror, are pretty much eliminated from this, and only options 1 and 2 uh, 1 and 2 are remaining here. So which one of them will be your uh, correct option? And all the other options are also locked here, because your option 5 is also objective lens, object 5 is also an objective lens here. So a simple way to go around it is, you need to excite a sample first to get an output from it, which will go through the mirror and then the detector. So typically your option 4 will be your excitation filter, and option 2 will be your emission filter. So the correct answer will be option number C, where 1 is your detector, this is your detector, this is your emission filter, this is your dichroic mirror, this is your excitation filter, and this is your objective lens. They are saying that it's MSQ, but only one option here is correct. Okay. What is the cut-on wavelength of the mirror labeled uh, DMLP 425T? So in any mirror, the wavelength cut-on wavelength will be signified by the numbers before the numbers in the mirror. So here it's written 425. So the answer is 425 nanometer. Okay. Last question, which is a multiple select question. Which of the following statements are true for Galvo scanner? It's a multiple select question. Which of the following statements are true for Galvo scanner? So last week we saw about galvanometric scanners, which produce positioning according to change in voltage. So the correct answer in this options are, so a galvo scanner provides superior positioning, speed and accuracy precision, and a dual axis galvo system contains two mirrors that reflects the incident light in x and y axis. So that's all the uh, I think the questions are for week nine's assignment problems. So till the I think we still have some time for the discussion for doubts. So till the end of the session, we can have some discussion of the doubts. If people have any doubts, they can ask it in the uh, chat box, or they can open their mic and then ask. If not, if people have any doubt, we can meet in week 11's TA session, which will happen next Sunday. That is on 5th April, in the same time. That is from 3 p.m. to 5 p.m. Yeah. But for now, the room will still be open for doubt session. So if people have any doubts, they can proceed to ask. Okay, if there are no doubts, we'll see you. I'll see you on next Sunday, 5th April, from 3 p.m. to 5 p.m.